Follow along while I do some recursion exercises. Here in number 1 we have a function f1 that is recursive, it calls itself. And we also have a function f2 that uses a loop. We would call that the iterative way of doing something rather than the recursive way of doing it. And the question is, for what values of n do both of these code segments, both of these methods, produce the same results? So let's plug in a number that's less than 0. And instead of like -1, let's just like shoot for a number that's a little deeper in the negative number line. Let's plug a -3 in here. So if we have the function f1 with a parameter -3, because -3 is less than 0, it quite simply just returns a 0. Let's plug a 0 in to see what happens with this function here. The f1 of 0, well, 0 is not less than 0, so that's false. So we execute this. The f of 1 of 0 minus 1 plus 0 times 10. All of that simplifies to the f of 1 of -1 plus 0. And we have already figured out that, well, when n is -1, it's 0. So 0 substitutes for all this. And we have 0 plus 0, which equals 0. And lastly, let's take a number that's greater than 0. Let's shoot for a big number like 3. So let's just plug 3 into the function f1 and see what happens. Well, simplifying that, because we hit this else case, this simplifies to the f1 of 3 minus 1 plus 3 times 10, which simplifies, of course, to the f1 parentheses 2 plus 30. We're not finished yet, so we have to figure out what f1 of 2 is. That simplifies to the f1 of 2 minus 1 plus 2 times 10. Don't forget, you have this plus 30 still coming along here to tackle on. But anyway, following the order of operations, this simplifies to 2 minus 1, the f1 of 1, plus, I'll just multiply that out now, that's 20. And of course, we still have the plus 30. Well, the f1 of 1, that, because 1 is not less than 0, that simplifies to the f1 of, well, I'm going to speed up here. 1 minus 1 is 0. So that's a 0 plus 1 times 10. That simplifies to this. In other words, this portion right here simplifies to all of this. Or I guess you could say expands to all of this. Don't forget you have the plus 20 still coming along, and you still have the plus 30. In general, I do not simplify these added on sums prematurely. I wait till the very end to do my adding or subtracting or dividing or whatever. Okay, the f1 of 0 we've already figured out that is really 0. So we end up with 0 plus 10 plus 20 plus 30, which simplifies to the number 60. So keep that keep record of this. But overall, we've now learned that the f1 of 3 is equal to 60. Now let's execute f2. Let's plug in these same numbers, -3, 0, and 3 for f2. I don't have much room here, but I'll try to squeeze it in. f2 of -3, well, that's equal to, since -3 is not greater than 0, all of this, the loop does not execute, and we return answer. And answer is initialized to 0. So that ends up being 0. Hey, it's a match. Check, check. For negative numbers, we know that room number 1 is one of our answers. Can I eliminate any of the answers here? Well, that rules out B, that rules out C, and that rules out D. So now it's a matter of whether both of these work or only one of these work. And to save time, I might not even bother plugging in both of these. Let's just do the f of 2. I'm sorry, I named it wrong. The name of the function is f2. So f2 parentheses 0, what's that equal to? Well, 0 is not greater than 0, so this is false. This loop does not iterate, and we again return answer when answer was 0. So those match up. Those two value results of f1 0 and the f2 parentheses 0 match. So we know that Roman numeral 2 is true under all conditions. So since Roman numerals 1 and 2 are both part of my solution, that rules out A, and I know that the answer here is E, without ever plugging in the value, a positive number, to f2. Well, anyway, you wouldn't want to waste time on the EP exam, but I will assure you that the f2 of 3 is equal to 60 if you were to trace this while loop. Question number 2 on this worksheet. We have mutual recursion going on here. Again, we have two methods, f and g. F calls g somewhere within it. G calls f. It's called mutual recursion. Well, let's figure out what the f of 6 is. And we need to figure out what the value of that is. Well, the f of 6, that's false, so we return the g of 6 minus 1. The g of 6 minus 1 is 5. I'm saving time here. Well, what's the g of 5? The g of 5, well, because 5 is not less than 0, we execute this. That simplifies to the f of 5 minus 1, which is 4, plus x, which is 5 at this moment in time. Now we have to analyze what the f of 4 is. So send 4 as a parameter up here to this x, and since 4 is not less than 0, this f4 part simplifies to the g of 4 minus 1, which is 3. Don't forget to bring the plus 5 along for the ride. And now what is g3 equal to? Well, send a 3 down here to this x. This is false, so we execute the else. All of this needs to be rewritten here for g3. This simplifies to the f of 3 minus 1, which is parentheses 2, plus x, which is currently 3, and this, see, this 3 is the parameter x. So that's a plus 3. And don't forget this plus 5 that's still coming along for the ride. Okay, so what's f2? I'll send the 2 up here. f2 is really the same thing as g of 2 minus 1. In other words, g of 1. Don't forget the plus 3 and the plus 5 coming along for the ride. What is g1? 1 is not less than or equal to 0, so again we have to use this. The f of 1 minus 1, which is 0, plus 1. And don't forget the plus 3 and the plus 5. What now is the f of 0? 0 is indeed less than or equal to 0. So we return 0 and never get to this part of the recursion. And that 0 plugs in for this f of 0. Don't forget the plus 1 and the plus 3 and the plus 5 that came along for the ride. Adding all this up because we're now finished. The recursion is finished. All of these plus 5s and plus 3s from previous stack frames, it sort of unravels and bubbles up to the top of this original f of 6. And this is really 9. Let's cross our fingers and hope that 9 is one of the options on this question. That is the answers. Let's see. Yes, 9 is an answer. That's D. Okay, number 3 on this worksheet. We have a function that's void, and it's also recursive. It calls itself, but it's a void function, which means it probably system out prints. Let's trace this one. Well, we start with recur7, and I'm just going to abbreviate here and just write R7. What does that equal? Well, 7 is not equal to 0. So we call the R of 7 minus 2, which is simplifies to 5. And we don't print anything yet. We have to now drill down and call R5 before we print. So there's work left to be done here. There's going to be some system out printing. There's going to be a system out print here. In fact, we're going to print n, which in this stack frame is 5, but not yet. So a 5 does print here. It's not really a question. The 5 prints, but only after we hit our base case and bubble back up. So that's not done yet. Okay, what's R5? R5, since 5 is not equal to 0, is the same thing as R of 5 minus 2. So that's the same thing as R3. And again, we have printing that we'll eventually do, but not yet. This number 3, no, I'm sorry. Up here I was wrong. It's the 7 that prints in the stacked frame eventually. And it's this 5 that's the parameter n that eventually prints. So we have a 7 eventually printing and a 5, but they haven't printed yet. Okay, this R3 drills down into stack frames, and it simplifies to 3 minus 2 is 1. And eventually we're going to print this 3, but not yet. R1 is next executed, and 1 is not equal to 0, so it changes into the R of 1 minus 2, which is negative 1. And the negative 1 then gets passed in as a parameter. Negative 1 is not 0, so that turns into negative 1 minus 2 is negative 3. And that, and there's going to be negative 1 will eventually print. Wait, hold on a second. I have no hope of hitting the base case. This will never end. We skipped over n being equal to 0. We keep doing this unless n, or until n hits 0, and n just missed 0. So one of these two are the answers. This is an example of infinite recursion. It's a logic mistake, but it is what it is. Now the question is, does anything print, or does actually nothing print? Well, nothing prints because we never hit our base case and bubble back up, allowing us through these stack frames in reverse order to get around to these system out print statements that are still sort of waiting on a to-do list somewhere. We never get to these system out print statements. We keep calling this method and never get back to this. So the answer is E. I guess you could argue that this eventually hits negative 2 billion with like the integer min value, but I don't think they're going to get that tricky here on this exam. So I don't think they're looking for that, and that's not a guaranteed thing. You don't know for sure if that's the way the compiler or the runtime unit works here. So let's go with the answer E. And, number 4. Number 4, we're calling this method mystery, which I'll just abbreviate M, with this big integer value, and we check to see what is this divided by 10. Anytime you divide by 10, it of course moves the decimal in one place and it chops off that value. So this, we're asking, we're not changing anything, we're asking if 12,345 is not equal to 0. Well, true, that is not equal to 0. So now we call mystery with whatever we do get when we divide this big number by 10. So we're calling it with the parameter 12,345. So this is really a 6 in there. I don't want to be sloppy with my handwriting. So this function call turns into this function call. Now there will be system out printing to do, just like in that previous exercise, but we're not getting around to it yet. What will eventually print? Well, whatever this number is, mod 10. And when you mod something by 10, you're really just stripping away the ones digit. So eventually a 6 prints out. I'm just saying, if we ever get there. Okay, well next we call this method, and if you chop off that 5, 1,234 is not equal to 0. So we really are calling the mystery of 1, 2, 3, 4 because of integer division that chops off the 0.5. And then eventually we'll be printing something. We'll be printing that ones digit, but not yet. And this then, in turn, gets called or executed. And we check to see if 123 is not equal to 0. It's not. So we call mystery of 123, eventually printing this 4 here because of the mod 10, but not yet. This in turn gets called, and we're executing the mystery of 12. Sorry about the sloppiness. We eventually will print this 3. The mystery of 12 turns into the mystery of 1 when you chop off that 0.2 that you end up with. Eventually we'll print that 2. And mystery of 1. When mystery of 1 gets called, a lot of students mess up here. What is 1 divided by 10? Well, you move the decimal point 1 place in, you chop off the 0.1, and you're left with 0. Is 0 not equal to 0? False. 0 is equal to 0. So 0 not equal to 0 is finally false, and we don't execute this recursive call anymore. So mystery 1 doesn't call this method again. Instead, it releases through and executes this line of code for the first time. But it does it down here in this stack frame. Now my next question is x, which is currently 1. What is 1 mod 10? When you have little number modded by big number, the answer is always little number. To see why, 1 divided by 10, what's the remainder of 1 divided by 10? 10 goes into that 0 times. 0 times 10 is 0. Subtract. You're left with a remainder of 1. That's what that just works out to be, so 1 is what we bottom out at. So we system out printed in our output window, we print a 1. And notice this is print and not print ln. So a 1 prints out. But now the computer hits this curly brace. So we're finished down here in this stack frame. We're finished printing the 1 that we just printed. The computer now bubbles back up through the stack frames in the reverse order that it delved down into them. So this 2, which back up in this stack frame, the parameter x was 12. And therefore 12 mod 10. 12 divided by 10 leaves a remainder of 2. That's just the way it is. It always works out. Remainder of 2. It's always the ones digit that you get when you mod by 10. So that 2, as we've already argued, that 2 finally system out prints. And because there's no print ln, the 2 butts right up against the 1. And then it backs up to this stack frame where x, the parameter x is 123, and this 3, because of the mod 10, the ones digit 3 prints. And so on. The 4 then prints, the 5 prints, and the 6 prints. There is your answer. That is what prints out when this code executes by this call statement. What the heck? It's the same number that we passed as a parameter to mystery. This isn't a very good method. It's not very useful, but it is what it is. So the answer here is C. That's what prints out. Number 5. We're calling recur32, and we're printing whatever the final return value is. So let's check it out. Let's abbreviate this to just R32. Well, we have this string called dig, and it's equal to the empty string being concatenated with the val mod 3. This is a little tricky here, but let's keep track of this variable dig. It's equal to something with val. What is val? Val's 32 at this moment. 32 mod 3, the remainder of this divided by 3, just trust me, the remainder is 2. Because 3 times 10 is 30, and you're left over with 2. So dig is equal to just the string 2. Now we check to see if val divided by 3 is greater than 0. What is this divided by 3? Well, 3 goes into that one time. We're left with like 10 point something, but because we have a slash, it's just 10. So 10 is indeed is greater than 0. So we are returning dig plus the recur of val divided by 3. Oh geez, we have to like call this again. I'm going to clean up my my scratch work here to write it a little bit more cleanly so that you can kind of see what's happening here. In stack frame number 1, we had val was equal to 32. And dig, we just saw, is equal to the string value 2. Now we are calling recur again. So this is stack frame 2. We're drilling down. Where val, what is 32 divided by 3? Well, we've already discussed that. That's the number 10 because it chops off the decimal places. And dig in this stack frame, when val is 10, dig is whatever you get when you take 10 mod 3. The leftover remainder, when you take 10 divided by 3, is 1. So dig is equal to 1 in stack frame number 2. And a 1 eventually will be returned, but we're not there yet until we call recur in stack frame 3, where val is whatever val was divided by 3. Well, what's 10 divided by 3? 3 point something, and the point something gets chopped away. So val is 3 in this stack frame. When val is 3, 3 mod 3 is a remainder of 0. So that is concatenated as a string. Java automatically turns integers into strings when you concatenate them with another string. Even though this is the empty string, it still turns it into a string. So the dig in this stack frame, number 3 here, is a 0. And I'm spacing them out on purpose over here to show you what happens in the end. Is val, is 3 divided by 3 greater than 0? Well, 3 divided by 3 is 0, and 0 is not greater than 0. So we 3 divided by 3. So we return dig. Okay, I think I made a mistake a second ago. I caught myself saying that 3 divided by 3 is 0. It's not. 3 divided by 3, in other words, val, 3 divided by 3 is 1. And 1 is indeed greater than 0. So we do execute this line of code, which says concatenate dig to the recur of val divided by 3. So we have to go to stack frame 4. And stack frame 4, 3 divided by 3 is 1. Therefore, the parameter val in stack frame 4 is 1. 3 divided by 3 is 1. It gets passed into this all over again, so it's 1. Now, what is 1 mod 3? Based on logic explained earlier when we had stuff like little number modded by big number, 1 mod 3 is 1. The remainder of 1 divided by 3 is 1. So dig in this stack frame number 4 is equal to the string 1. And we check to see what val divided by 3 is. Well, 1 divided by 3 is 0.3 repeating, 0.333. But it chops off the 0.333 because of integer division with this division symbol. So it really turns into if 0 greater than 0. Well, that's false. And we, for the first time, ignore this line of code. We don't go to a stack frame number 5. This was really stack frame 4, sorry about that. We don't go to stack frame 5. We now fall through and execute this. Well, because this was string concatenation and not normal addition, we return dig, which is 1, the string 1, back up to the previous stack frame. And because all of this was on the right-hand side of this plus symbol, in the previous stack frame, this 1 gets concatenated from the right side to this 0. This 0 sort of glues together with this 1, and since they're strings, they get glued together with string concatenation. So they go together to form the string that looks like this. And then that stack frame number 3, falls through and executes where it left off. It returns dig plus all of this. So this 1 here gets joined on to the 0, 1. Again, the 0, 1's on the right, and this dig, the 1 here from the stack frame, is on the left. So that goes together to be this bigger string. And then it bubbles back up to this stack frame number 1, where this 2 joins this from the left, and we end up with the string 2101. Not the number 2101, but the string 2101. The answer is E. This was tricky, 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 tricky.